Now, in this video, we will going to discuss one more type of load, which is the uniformly varying load. So, draw the SFD and BMD for a cantilever beam with a uniformly varying load, which is UVL. So here, since it is a cantilever beam, so one end of the beam is fixed and the other end is free, and the load is acting on the uniformly varying from 0 at B and W per unit length at A. So here, figure shows a cantilever AB of length small l. So this is the length of the beam, which is fixed at A and free at B, carrying a uniformly varying load from 0 at the free end and W per unit length at the fixed end. So what are the reactions which you will going to get at the fixed end? So one is horizontal load which is coming on the beam will going to be 0. Sigma h is equal to 0. Since there is no horizontal load on the beam, therefore RA which will be always equal to 0. So then algebraic sum of all the forces acting in the vertical direction should be equal to 0. So that is sigma V will be equal to 0. So what is that? Total load on the beam will be equal to area of the triangle. So which is the area of the triangle? That is A, B and this W what we have. So for the entire length. So that is what is the area of the triangle? Half into base into height. So what is half? Half into base is L and the height is W. So half into W into L. So half into W into L. So this will going to be the area of the triangle. So that is the total load on the beam. Therefore, RAV, that is sum of the load, which is sigma V will be equal to 0. So therefore, the load acting upward direction is positive. So RAV minus the load acting downwards is negative. Minus half into W into L. And you transfer this half into W into L to the right hand side. Therefore, the reaction at A in the vertical direction will be equal to half into W into L. So this will going to be RAV, which will be equal to half into W into L. So what is the algebraic sum of the moment will be equal to 0. So what is that? Taking the moments about the point A, which will going to be here about A will be equal to 0. So that is the reactive moment as the load is acting from the upward direction. So on the downward direction. So naturally the load will be acting, so it will be clockwise, and the reactive moment will be always in the counterclockwise direction. So therefore, in order to keep the body in equilibrium. So what is that? Minus MA plus what will going to be the moment here? The load which is acting on the beam. So that will be area of the triangle half into W into L and the distance of center of gravity from the bigger end, which will going to be 1 by 3 into the distance from the bigger end. So that will be 1 by 3 into what will going to be the length of the beam, that will be L into L. So therefore, minus MA plus it is in the clockwise direction. So plus half into area of the triangle, half into W into L, that is the area of the triangle, into the distance of center of gravity from the fixed end, which will going to be from the bigger end, which will be 1 by 3 into L. So that where it will be 1 by 3 into L. So since L into 1 will be equal to L, so that will be equal to L by 3. So therefore, when you are considering this, you take MA to the right hand side. Therefore, the moment about the point A will be equal to W into L square by 6. So W into L square by 6, which is the reactive moment at A. MA will be equal to WL square by 6. So that is how we will be able to find the reactions at A, both in the vertical direction and the horizontal direction, and also the reactive couple or the reactive moment, which is MA, which will be in the counterclockwise direction. Now we are going to take up the shear force. So when you are trying to consider the shear force, consider a section which is XX at a distance X from X from V. So what is the rate of loading of L? So the rate of loading of L will be equal to W. So rate of loading for the length X will be equal to W into x by L. So how to find out this? So when you are considering the section XX, you can see here there is two similar triangles. One triangle is between A to B and to this W. So this is going to be the one triangle. And the other triangle is the distance XX into the height XX into X and this triangle B. So here, by the application of similar triangle principle, so what happens? This distance, that is A to W divided by EB, will be equal to XX into the distance of this section XX from the point B, which is X. So to do that, so this is W by L will be equal to W by L will be equal to, so this height, which is XX by X. So naturally what happens if you say XX, so that will be equal to W by L equals XX by X. So W into X by L will going to be this height. So that is what we have written here, W into X by L. So that is the rate of load for the length X. So shear force at the section XX if you are considering. Now what we need to know is, so what will going to be the shear force at this section XX? So for that, so what will be Fx will be equal to, you are considering only the area of the triangle. So area of the load diagram between XX and B, so that will be equal to half into base into height. So what is the height? Wx by L. So half into Wx by L into the base, which is X. So therefore, you will going to get it as W into X square by 2L. So as we see in the equation 1, the power of X is 2. Therefore, what happens? Therefore, SF is positive as the right of the portion slides downward with respect to the left portion. So therefore, when the value of X is equal to 0, so what happens? SF at B will be equal to 0. When the value of X is equal to L, what happens? SF at A. So substitute the value of L in the given expression, that is Wx square by L. So in such a case, you will going to get it as half into W into, put the value of X is equal to L, which will be L square by L. So that will be equal to half into W into L. Therefore, SF at A will be equal to half into W into L. So since it is the positive value, so you are taking this from this, half into W into L. So when you want to join between the point B and to this point, WL by 2, so what is the nature of the curve? Since the power of X is here is 2, so naturally the curve what you have to get between these 2 points will going to be the parabolic curve, because it is acting. So here because the term of X will be to the quadratic expression, which is the power is 2. So that is how you will be able to analyze this by using the shear force, and this is the plot what you will going to get. So join between the point B and join between the point B and also with W into L by 2. So join these two by means of a smooth parabolic curve. So this is how you will be able to analyze the shear force diagram. So therefore, the variation of the shear force is in the form of a parabola. Now we are going to consider the bending moment. So what is the bending moment? Bending moment at the section XX, if you want to consider. So here, what is that? Mx will be equal to, so what happens? Area of the triangle into the distance of center of gravity from the bigger end. So the moment when you are considering the moment of bending moment at the point XX, so this will go to be the bigger end and this will go to be the smaller end. So what is that? Since it is a triangle between XX and B, so naturally half into the base is X into height is Wx by L. So minus half into the base is Wx by L in Wx by L into the base height is Wx by L into the base is X. So minus half into W into X into X by L. So into the distance of center of gravity from the bigger end, which is equal to X by 3. So that is divided into x by 3. So when the value, so that will be wx minus wx cube by 6L on simplification. So call this equation as 2. So here the bending moment is negative as the moment of load taken from the right of the section xx is clockwise and the bending moment is hogging. So that means they try to bend in the downward direction because to the load acting from the upward direction. So therefore, the tendency of the beam to get bent in the hogging style. So therefore, you are going to get a hogging bending moment. And also, since the power of x in this expression is cube, as from the equation 2, the variation of bending moment is according to the cubic law. So naturally, the curve what you are going to join between the point B and to this point W will going to be the cubic law. So when the value of x is equal to 0, substitute the value of x is equal to 0 here, then at x is equal to 0, the bending moment at the point B will be equal to 0. Bm and B will be equal to 0. Similarly, when the value of x is equal to L, then bending moment at the point A will be equal to, you substitute the value of x is equal to L here. So that is minus WL cube by 6L. You cancel 1L and 1L. So that will be minus WL square by 6. So the bending moment at the point A will be equal to minus WL cube WL square by 6. So substitute that, you will going to get it as cancels these two, L square, L cube and L will go to be gets cancelled. So that will be equal to minus WL square by 6. So when you plot this, what happens? At the point B will be equal to 0 and at the point A which will be WL square by 6. So here W minus WL square by 6. So then join between these two curves. When you join between these two, the curve what you will going to get, it will going to be the cubic power. So this is the variation of the bending moment in the negative direction. Here it is not minus W into L the whole square by 2, it is minus WL square by 6. So this is the value what you will going to get at the point B. So this is how you will be able to analyze the uniformly varying load in the cantilever beam. Thank you.